Yes.
Okay. Where are you, William? Truth is not. Oh, William here. William, you have the permission.
No, it still says I need to ask the host.
Well, you see that it's William Sirigar. Is it your last name?
Yep, that's the one.
Okay, and if you see here, I gave you the permission, and here it tells me remove the permission. So probably your recording is not set up correctly, but otherwise I gave you the permission.
Okay, all right, thank you.
And this time I'm just missing Juan Dominguez and Jason Yu. Hopefully they are fine and will join us quickly. Let us put these aside. And every discussion we have is shown in these slides. And also, you have your textbook, and most of the material, except the few first chapters, are taken from your textbook. The time that theory of elasticity was written by Timoshenko at the time, 7-8 years ago, still the stress and strain concepts were being developed, in particular in terms of tensors and so forth. So that's why I provided these couple of chapters. Those who had advanced mechanics of material with me, probably last semester or so, they were exposed to these concepts. So it would be a review of what we learned before. And the next thing I would like to remind you is that the homework problems that I assigned for you guys last week is due by the end of today, that is midnight today. If you want to get the perfect score, and the solution will be provided then. Please work on these homework problems and let me know if you have any difficulty understanding the subject. So just reminding you again, the due time will be by the end of today. Put as many problems as you worked on. It's only 10 problems. And let me see if you have any difficulty. I have Juan Dominguez not joining us. There you are, Juan. So only one missing is Jason. All right. I have Jason Yu with my composite course this morning, so he should be all right. And maybe joining us soon. Anyway. All right. Last couple of weeks, probably we talked about the basics of stresses and how we can define stress in terms of its component, in particular tensor components in a two-dimensional and three-dimensional space, and rule of transformation of these tensors. Now we are going to talk about this week about strains and deformation. Generally, let us consider a deformable body as shown here, which is subjected to some external loads, and consequently points in that object would be displaced to a new position, and the body itself would deform from an initial shape to a new shape. Consider a point such as point A on the body and a point B as well on the body. Connecting these 2 points, it will be a straight line AB. Now, as a result of loads being applied, these points will be displaced to point A prime and B prime. And as you can see, the displacement in X direction is shown with the letter U, and the displacement in Y direction is shown with the letter V. The picture is a two-dimensional deformation, but if we have a three-dimensional deformation, naturally displacement in Z direction will be also be defined with W. Similarly, point B moves to a new position B prime with the displacement U prime, V prime, and W prime. It's just a simple displacement. That displacement could be the result of deformation of the object, or simply as a result of rigid body motion of the object. If the body is just being displaced from one location to the other location without any deformation. So be careful with the displacement as being defined. It doesn't mean deformation of the body. It comprises both the deformation as well as rigid body displacement. If it's a deformable body, if the body is being deformed due to the loads applied, due to the stresses applied, then the line AB will not be equal to the line A prime, B prime. Therefore, there will be some change in length, and that change in length represents the deformation of it. Displacement at any point can be expressed in terms of the coordinate system X, Y, Z. For example, at point A, displacement would be U, X, and Y, and Z. That means U as a function of X and Y and Z. And obviously, when we go from one point to the other point in the object, the displacement varies. And if the coordinates of that point is given, these equations should provide you the displacement of those locations. A solution, a final solution of a elastic body under external load should provide you with the displacement equations that show how much each point would move from one location to the other. Generally speaking, in all of our engineering work, displacement is very small. Displacement compared to the overall dimension of the body is small. If you are talking about having, for example, a beam, a 1,000-ton load is being applied at the middle of that beam, the beam deforms, but its sagging, its deformation, its displacement over the center point compared to the length of the beam is at least a couple of order of magnitude smaller. Most of the engineering problems are solved in that fashion. Although there are specific problems and specific designs that deals with non-small displacement, where displacement is large. An example of that would be a very thin plate that you load it laterally, and the displacement there compared to the thickness of the thin plate is not negligible. It may be even larger than the thickness of the plate. Theory of elasticity that we talk about today deals with the problem only when displacement is small. It is small compared to every dimension of the body. And let us define strain as a measure of the formation of an elastic body, similar to stress that is a measure of internal load, intensity of internal load. Strain would define the intensity of internal deformation. Let us first consider a one-dimensional body where a rod that has initial length of L0, as shown on the picture A, and it's being loaded along its length, and it deforms, as shown in the picture B. Its length from L0 increases to L. Consider a point A at the distance x from the top, and as the deformation occurs, as the load is being applied, point A moves to a new position A prime, and displacement of that point is shown with U. A neighboring point such as B at the distance delta x from point A moves to a new position B prime, whose displacement would be, of course, increased from U to U plus delta U, a little bit more than the displacement of point A. Delta in this picture shows the total elongation of the rod after the load is being applied. Now, as we mentioned, A goes to A prime, displacement is U. B goes to B prime, displacement is U plus delta U. Initial length of AB is delta x. Now, the final length of A prime, B prime, you can see it would be delta x plus delta U. That is U plus delta U minus U plus delta x initial length. Strain in x direction, longitudinal strain, epsilon x, is defined as the initial, the final length, A prime, B prime, minus initial length divided by the initial length. Change in length over the initial length. And substituting these into that equation, you would find that epsilon x is simply derivative of displacement in x direction with respect to x. So that is the relationship between the displacement and strain. Strain epsilon x is simply derivative of deformation in x direction with respect to x. This is the definition of the small strain, or the definition of engineering strain, when initial length and final length are very close to each other. In these cases, epsilon x, or the strain, would be in the range of 0.001 or 0.01 maximum in majority of the cases of elastic deformation. Very small number, small strain problems. If we are dealing with, for example, a material like rubber, or we are dealing beyond the elastic limit, you are stretching an aluminum rod and its length due to the load applied could be doubled. So engineering strain would be almost equal to 1. In this case, it doesn't make sense to use the concept of engineering strain, and we are talking about usually true strain. True strain is defined as its differential dl over L. That is, we are not going to subtract initial final length from initial length divided by initial length, but we look into the picture at instantaneous time. After the load applied, the strain would increase gradually, and its strain d epsilon differential of strain would be defined as dl, change in length of one element over L. If I integrate that, I come up to the definition of true strain. true strain, as you can see, is equal to logarithm 1 plus engineering strain. I've shown a picture on the right-hand side and show what's the difference between these two. Engineering strain of 1 correspond to a true strain of 0.69315, about 30% higher than the true strain. But if you are talking of small strain, 0.001, there is no difference between the engineering strain and true strain. Even if you take the strain 0.01, the difference is negligible. Even at 10% strain, the difference between the true strain and the engineering strain is less than 5%. So for most practical purposes, as long as we are dealing in elastic limit, strain is small. However, if the case is to study the plasticity, you cannot work with engineering strain. We have to consider true strain. And that reminds me, when we were working with the finite element methods and studying some structures when I was working at Boeing, some novice programmers and engineers working with these finite element methods, and especially the customers on the other side, did not realize the difference between these true strain and strain, engineering strain. So, for example, for the aluminum, you look into the table, you look into the handbooks, aluminum, say 6061 T6, has this specific property, and you write down that stress-strain relationship for that aluminum from the handbook in front of you. However, that strain that you read from the handbook is engineering strain. That cannot be fed into the finite element formulations if you are working beyond the elastic limit, if you are working in plasticity limit. So if you are working with the plasticity and nonlinear system in general, you have to use the true strain, and the relationship between the true strain and the engineering strain are given here. Let us move to the next slide. Okay, going from 1 dimension to 2 dimension, again, we consider a block. In bottom, on the left-hand side, we have a rectangular element, uppercase A, B, D, C. This block here, A, B, D, C, whose length in X direction is dx, and in Y direction is dy. Location of every point on that block is given by the coordinate system with respect to XY coordinate system. Location of point A is given X and Y. Location of point B, which is at a distance dx from point A, would be just a little bit different, x plus dx. And similarly, C, location would be a location at point A, which is in Y direction, which is y plus dy. Now that block is deforming due to the external loads into the shape shown on the right, which shows both deformation and displacement and change in shape. The rectangle becomes this trapezoid, whatever shape it is. Now, I can look into the picture and see the displacement of point A to new position, lowercase a, is u, and it's a function of the position x and y. And the vertical deformation of that is shown with v. So u and v are displacement of point A. A neighboring point B along the x-axis would deform to a new position B, whose total displacement would be u x plus dx and y, and the difference in the length along the x-axis would be derivative of u with respect to x dx, and along the y-axis, derivative of v with respect to x dx. Similarly, in the other direction. It is simply graphical presentation of the formation of a two-dimensional body. So if I am interested to calculate the strain, I have to see how much AB changes to the lowercase ab. So the difference between the length of AB and the lowercase ab would show the strain in x direction and similarly in y direction. In y direction, initial length dx. In x direction, initial length dx. In y direction, initial length is dy. Now, length of AB, this new shape here, from the geometry of the, let me get my pen, just a little bit. From geometry of this triangle, wrong pen choosing. You can see that length of AB is dx plus derivative of u with respect to x squared plus derivative of v with respect to x squared. Just looking into that triangle. Expand this term, I come up with this expression. And notice, as we indicated before, displacement u and v are very, very small. Therefore, anything into power 2, as shown here, compared to something into power 1, is negligible. If u, for example, or derivative of u with respect to x is equal to, say, 0.01, the power 2 of that derivative would be 0.0001, 100 times smaller. So we can actually ignore the second term here, the derivative of u with respect to x into power 2 and derivative of v with respect to x into power 2. So these two last terms could be ignored, and then that square root can be expanded using the Euler equations, and it could be simplified as 1 plus 2 derivative of that square root becomes 1 plus derivative of 1 plus derivative of u with respect to x. So substitute that one for that square root. This is the new length. Subtract them from the initial length. You come up basically to the same equation that we drive for one-dimensional problem. If the displacement is small, the engineering strain is related to the displacement by this equation. Derivative of u with respect to x would be epsilon x. Similarly, if I walk in the other direction, I can show that the epsilon y is derivative of displacement in y direction with respect to y, and the partial derivative of w with respect to z gives you the strain in z direction. Looking into the same picture, I can define the shear strain. Shear strain, engineering shear strain, is defined as change of the angle, total change of angle. Initially, the angle between AB and AC is 90 degrees. Now, after deformation, it is reduced to the new angle, and the change is equal to alpha here, the angle alpha here, with respect to x, plus angle beta with respect to y. So the total shear strain gamma xy is equal to alpha plus beta. Now, from this picture, again, similar to what said before, I can calculate tangent of alpha, derivative of u with respect to x dx, plus dx, plus derivative of u with respect to x dx. And simplify, we come up to this equation, and similarly angle beta. And notice that in this case, again, the displacement u and v and w are very small, and therefore in the denominator I can ignore this derivative compared to 1 is small. I can neglect it, and the tangent of alpha becomes derivative of u with respect to x, and tangent of beta will be derivative of v with respect to y. And because it is a very small displacement, tangent of alpha would be a small number, and it would be approximately equal to alpha. Tangent of beta would be approximately equal to beta. So from this equation, we see that gamma xy, alpha plus beta, would be equal to this expression. Actually, by this I mean derivative of u with respect to x plus derivative of u with respect to y plus derivative of v with respect to x. So at the end, in three-dimensional space again, we can define the strain components, normal components of strain, epsilon x, epsilon y, epsilon z, as derivative of u with respect to x, y, and z. And the shear strain are defined as derivative of u with respect to y plus derivative of v with respect to x, and so forth. Notice from this definition, from the very technique of information given, gamma xy should be equal to gamma yx, because if you replace the position of x and y, you end up with the same equation. Similarly, gamma yz is equal to gamma zy, and gamma zx is equal to gamma x. This is exactly similar to the stresses from several points of view. Stress, we indicated to be a tensor of second degree, and a three-dimensional space are identified by 6 components: sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. Strain in three-dimensional space also are identified with 6 components: 3 normal component, epsilon x, epsilon 1, epsilon z, and 3 shear component, gamma xy, gamma xz, gamma yz. Similar to the stresses, these strain matrices are symmetric. Gamma xy is equal to gamma yx, similar to tau xy is equal to tau yx. So the question still remains if the strain are indeed tensors of second degree. If they are a tensor of second degree, we should show that the same rule of transformation from one coordinate system to another coordinate system, as we explained for the stresses, would be applied for the strain as well. However, our work shows, our later work shows, that to define the strain as a tensor of second degree, we need a little bit of adjustment. Basically, strain should have been defined by the equation shown on the top. Epsilon ij is equal to 1/2 derivative of ui over derivative of xj, derivative uj with respect to xi, where I and j in this equation would be x or y or z. So when I say derivative with respect to xj, it means derivative with respect to x or y or z. When I am talking about x1 and x2 and x3 in this equation, I mean x and y and z. That's the way we define in a tensor notation. And similarly, ux and uy and uz are u and v and w as we define for the displacement in x and y and z direction. Look at this equation. And for example, assume I and j are equal and they are equal to x. So ij equal, that means it's epsilon xx is equal to 1/2 of u, partial derivative of ui, and I was x, so it would be ux with respect to x, partial derivative of y, that should be y actually, with respect to, oh, that's x, so that's the same x, because we are dealing with I and j equal to x. So again, derivative j is equal to x as well, so it would be derivative of ux with respect to x. These two would be equal, so they are added together. 1/2 of this plus that would be just derivative of u with respect to x. So when I and j are equal, for example, equal to x, it would give me the same solution that we have introduced before. So epsilon xx would be equal to epsilon x. If I and j are different, one is equal to x, the other one is equal to y, if you work through that equation, you can see that now the shear strain in strain notation, in tensor notation, would be 1/2 of the shear strain in engineering notation. So if we want the same rule of transformation applied for the strain, we have to make the strain matrix as shown in the bottom. Normal strain are as it was before, epsilon x, epsilon y, epsilon z do not change. But the shear strain in this matrix should be replaced with 1/2 of shear strain. If we put them in this fashion, then it can be shown easily that the strain as well follow the same rule of tensors of second. So remember, tensor matrix is made by considering epsilon x, epsilon y, epsilon z as before, normal strain as before, but the shear strain are actually 1/2 of the engineering shear strain. Moving on. As far as we talked about we were talking of the small displacement and small strain. So if the system is linear, we can use the concept of superposition. That means if I apply the load of 10 kilogram force on the body and measure its deformation at location 1, and it is 1 millimeter. Now, if I double the force, the formation at that point would be as well doubled. When can we apply the rule of superposition? Superposition rule can only be applied if all these three conditions indicated are satisfied. First, displacements are small. Loading configuration will not change after the deformation. Second, strains are calculated are small. And thirdly, stress-strain relationship, deformation versus load applied, is linear. So it's not to perhaps surprise of some people, the system is not linear, or superposition principle cannot be applied if only you consider the material is linear. So even if you work within the elastic limit, if the displacement large, if the strain is large, the system is not linear and you cannot apply superposition. Consider the case of buckling. If I have a beam, you learned it before, and I apply the compressive force here, as long as the load is small, I have only compressive stress developed here, sigma equal to P over A, where A is cross-section of this part. But as P is increasing, the beam at a moment will buckle. So assumes a new shape. And in this new shape, the loading equilibrium would be different from initial shape. When it is being deflected as such, due to the presence of the load P, I don't only produce axial load, but because of this distance, say y, I create a bending moment equal to Py. The larger the displacement, the larger the moment. So stresses and deformations and the strain would be a function of the deformation of the material. That is to say, the loading would be different than initial loading we assume in the beginning of the problem. In this case, the system is not linear and the principle of superposition cannot be applied. Now, probably some 100 years ago, when equations of theory of elasticity were put together, many scientists discovered that there should be certain relationship between these components of the strain, gamma x, epsilon x, epsilon y, gamma xy, gamma epsilon z, gamma xz, gamma yz. There are 6 components of the strain. that are defined from three components of displacement. We have U, we have V, we have W, and from these three components, we developed the equation for epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, and gamma yz. Therefore, from three expressions for the U and V and W, we came up with 6 expressions for the epsilon x, epsilon y, epsilon z, gamma xy, gamma xz, gamma yz. All of these shapes would not be independently formulated in terms of the displacement. So there should be some relationship between these strengths in terms of the displacement. Let us look into the equation. Epsilon x is partial derivative of u with respect to x. Let us get the second derivative of this expression with respect to y. So derivative of epsilon x with respect to y twice would be the derivative of this term with respect to y twice, and that's what we did. The second equation defines the epsilon y derivative of v with respect to y. Let us get the derivative of this equation on both sides with respect to x twice. So I end up with second derivative of epsilon y with respect to x is equal to, look into that equation, get the derivative with respect to x twice. So we end up with that expression. Let us add these two expressions. Therefore, let us look into also gamma xy and get the derivative of gamma xy once with respect to x and once with respect to y. So get the derivative of this term with respect to x and with respect to y, derivative of this term with respect to x and with respect to y, we end up with these two terms. Adding these two and comparing with this equation, we can see this plus this is equal to this. This is the first compatibility equation that tells us the second derivative of shear strain with respect to x and y is equal to the second derivative of epsilon with respect to y plus the second derivative of strain in y direction with respect to x. This is the first compatibility equation. Working in a similar mathematical way, you can find additional 5 equations of compatibility. So in total, we have 6 equations of compatibility that correlates all these 6 components of the strain to the derivatives of one another with respect to x, y, and z. As I've mentioned, these equations were first introduced by Barré de Saint-Venant in 1864, over 150 years ago, perhaps. That's why we have many theorems named after Saint-Venant.
Professor?
Go ahead.
Are you going to cover large strain formulation? Because that's what's on the slides and Canvas.
Say it again.
Are you going to cover large strain formulation?
Yeah. Let me go to the next slides and I'm talking about that.
Oh, okay. Yeah, it's because the slides on Canvas we already passed that if we're going based off those slides. That's why I was curious.
Okay.
All right, thank you.
There may be some correction. Let me, one thing I would like you guys to notice is that I put these slides together as we go through the course here, and I do some correction and modification. So you don't need to print the slides that are presented. I would rather look at them because we are modifying it from time to time. And I really appreciate if you find some error in this formulation, let me know so we can make a correction accordingly. So these are the compatibility equations. If these equations are not satisfied, the final deformation would not be will not be compatible. We will have interference from one section of the body to the other section, or we will have gap or holes produced in the system. By the way, most of our mechanics of material problems that we solve in our undergraduate programs, theories of bending, theories for the axial loading or torsion, most of these problems are simply looking into equilibrium of the stresses and external forces. So we satisfy equilibrium conditions. We do not usually satisfy the compatibility equation. These 6 equations that are mentioned here are not satisfied. So that's why all the solutions we have in simple mechanics of material would be only valid approximately. Sometimes approximation is good enough, sometimes it's not. And as we go through the theory of elasticity, we can see benefits of formulation based on elasticity as compared to those basic theories in mechanics of material. Yeah, this is the large strain that I missed here. Let us talk about large strain. Basically, theory of elasticity that is being formulated and we are discussing in this course is based on small strain and small displacement. Other theories are being developed nowadays, working with large strain and large displacement. Specifically, if you're running a finite element software, you will see there, for example, in that software boxes that are asking you, is this a small displacement? Is this a small strain? You can check those boxes and jump from simple linear small strain, small displacement case to a large strain or large displacement cases, and the formulation will be different. So the formulation for the strain that is taken by these finite element softwares for large strain are given by this equation. Strain in X direction is defined as the final length into power 2 minus initial length into power 2 divided by 2 times the initial length into power 2. That's epsilon x. If epsilon x is small, this definition would be identical to the definition we had before. How is it identical? So if length AB squared minus length AB squared is the difference small, you can write it as say length AB, I just put A instead of length, minus length AB, and you factor length AB plus length AB divided by 2 length AB. If the strain is small, length AB and length AB capital, initial length and final length, would be almost identical. One is 1 meter, the other one is 1.001 meters. So they are almost identical, and it would be equal to 2 length, initial length AB. So that 2 with that 2 cancels out, and this is into power 2. So one of these would go with the power 2, and we end up with the same definition, change in length, with divided by initial length, as we define the strain for the large, for the small strain. So this definition is compatible with small deformation, because when you are introducing a large strain deformation, it should also cover small deformation to have a continuity in our formulation. Now, looking into that equation, initial length, as we have given before, is in terms of the displacement, and you substitute there, you end up with this equation for the strain. Similarly, in y direction, and similarly for the shear strain. So this slide shows the strain when large strain formation is considered. You can see the additional second power equation are added to the initial equation that we had.
Professor?
Yes.
I'm just curious, if we're running a finite element model and we turn on large deformations, since it cancels out, just like you just showed there, back to a small strain, does it cause any error if your simulation has small strain in it, but you turn on large deformation? Does that make a difference?
No, if it is a small displacement, first of all, we are not talking of displacement, we are talking of strain. If it's small strain, the large strain formulation should give you the correct answer. But it should take longer, for example, because the system becomes nonlinear. Solving these equations would be would take much longer time, and it is done by iteration, and we may end up with situations that it may not converge, and we have to work through the problem. So a problem that may take few seconds, if we are assuming a small strain, may end up a week or two working to arrive at a reasonable solution for large strain. But if we mistakenly, for example, assume large strain and use these equations in place of the small strain, we should come up with the correct solution.
Okay.
On the other hand, if the small strain is not the correct assumption and should have been a large strain, if you use the linear system and small strain condition, then your solution wouldn't be accurate.
Okay, thank you.
Okay. One thing I would like to show is what is the rule of transformation for the strain. Assume I have a rectangular shape of the length delta S in either case, and the load is applied, and the length in horizontal direction changes to delta S 1 plus epsilon x, where epsilon x is strain in x direction, and the vertical length would change delta S 1 plus epsilon y, where epsilon y is the strain in y direction. And the change in angle here, the new angle here, would be pi over 2 minus gamma xy. So gamma xy can be calculated from this angle, subtracted from 90 degrees initial line. So consider, as it's mentioned here, a square element with the center at 2, which is parallel to xy coordinate system. Now we are applying the load, and after deformation, we arrive at that parallelogram picture. That one side is delta S1 plus epsilon x, the other side delta S1 plus epsilon y, and the change in the angle is pi over 2 minus gamma xy. This smaller angle and the larger angle pi over 2 plus gamma x. So this shows the deformation of the element. This shows how the dimension change, how the angle change. But separate from that deformation, the element also goes under some rigid body displacement, which is not relevant to the strain. Rigid body displacement will not cause strain in the system. Now, consider the same element that we introduced before, that whose strain were measured with respect to xy coordinate system. Now, if we choose a new coordinate system, which makes an angle theta with respect to all coordinate system, the question is that what would be the epsilon prime x, epsilon prime y, gamma x prime y prime with respect to this new coordinate system. So the aim is to define the strain with respect to the new coordinate system, and it is in a similar background that we had with the case of stresses. To do that, very similar to the case of the stress, we consider a element ABC, this triangular element, where the side AB makes an angle equal to theta with respect to x-axis. The question is that if I have strain along AC defined by epsilon x and strain along BC, which is defined by epsilon y, what would be the strain along AB after the deformation is applied? You can make those definitions based on the strain that we defined before in previous slide. The side AC becomes A prime C prime, whose length is delta x, 1 plus epsilon x. The side B prime C is delta y, 1 plus epsilon y. And the angle here is the shear pi over 2 gamma xy. Now on the triangle A prime, B prime, C prime, we can use the rule of cosine and calculate the length A prime, B prime. And that's what we did here. A prime, B prime square is equal to A prime, C prime square plus B prime, C prime square minus twice A prime, C prime, B prime, C prime, cosine of the angle here, which is pi over 2 plus gamma x. Simplify this equation, And notice for small angles and small strain, the sign of the shear strain would be equal to the shear strain, and make other substitution and mathematical simplification. You would see that the strain in the new direction, A prime, B prime, is related to the strain in the old coordinate system through this equation. Change X prime to another direction, and notice you get the epsilon Y prime, and notice the relationship between cosine 2 theta and cosine of 2 theta. Write that mathematical relationship, you end up with this familiar equation that defines strain in X and Y direction with respect to the new coordinate system. Shear strain transformation may not be that easy to define from those triangles shown, but we can show that shear strain is related to the strain in 45 degrees. Consider strain along a line that is forming an angle 45 degrees with respect to x-axis. Then epsilon at 45 degrees from this equation on top. If theta is equal to 45 degrees, epsilon 45 degrees is equal to 1/2 epsilon x plus epsilon y plus gamma xy, because cosine and sine of 45 degrees is square root of 2/2. Substitute there, it simplifies to this equation. So from that equation, you can see gamma xy is equal to twice cosine epsilon of 45 degrees minus epsilon x plus epsilon. Now consider an element that makes an angle equal to 45 degrees with respect to x prime axis. You end up with a similar equation that we have shown here. Anything on top with a prime in the bottom. Epsilon prime 45 degrees is equal to epsilon with respect to theta plus 45 degrees. Expand that expression and simplify and substitute into the equations here. You end up with this relationship that gives you the shear strain in the new coordinate system as a function of the components of the strain in XY coordinates. Putting them together, we end up with these three equations that you are all made familiar with in mechanics of material in prior courses. But one thing we notice, if we replace gamma xy divided by 2 and use the tensor notation, instead of gamma x divided by 2, use epsilon xy, or use 1/2 of the shear strain, the formulation on the top would be identical to the formulation that we developed for the stress, and therefore the rule of transformation that we indicated for two-dimensional problem would be here in a similar fashion applied for the strain. Strain in the new coordinate system, epsilon prime x, and here 1/2 of gamma prime xy, a symmetric matrix, and epsilon prime y is obtained by multiplying the transformation matrix into dimension by its transpose. And here in the middle, we have the strain in the old coordinate system. Remember, it is a similar equation that we had for the stress, only we have to replace gamma xy with 1/2 of gamma xy. Similar formulation can be developed in a three-dimensional space. We come to that, but before going there, very similar to the stresses, there is always possible to find two mutually perpendicular directions with respect to which strain are either maximum or minimum. And the maximum and minimum strain are calculated through this equation, which is very similar to the stress equation, except that gamma xy over 2, or 1/2 of gamma xy, is replacing the tau xy as the case with the stress. Gamma xy can be also expressed in terms of the principal stresses 1 and 2. Here on these slides, I have put together another format to prove the same relationship that we derived previously. I'm going over that. You are welcome to glance over to this and see if you arrive at the same formulation. So, very similar to the stresses, we have principal strains, epsilon 1 and epsilon 2, which are either maximum or minimum as the coordinate system rotates. And when we have the principal strain, in those directions, the shear strain would vanish. Shear strain would be 0. And we can find the direction where the shear strain are maximum, very similar to the case of the stresses, that will be at 45 degrees with respect to the principal strain directions. In a similar fashion that we did for the stresses, we can use the Mohr circle. And that graphical presentation is shown here. The only difference here is on the x-axis, we have the normal strain, as shown here. On the y-axis, we have 1/2 of the shear strain. Give you an example here, an element for which its plane strain values are given, epsilon x, epsilon y, epsilon gamma xy. We want to see that what are the principal strains, what's the maximum shear strain, and strain in with respect to a coordinate system that makes an angle 30 degrees. We can use the equations given here. This equation to calculate strain in the direction that is shown, and these are the values. We can find when it is maximum, what angle and what value would be the maximum and minimum based on the equation given. Or we can use the Mohr circle and graphically present that. It would be very similar to the case of the stress. So rule of transformation for the strain are depicted as shown in this slide. The formulas here that we learned on the top from usual mechanics of material, and formula in the bottom that gives the same equation, but in the form of the tensor transformation. A similar relationship can be defined for a three-dimensional case, and we have shown that for the stresses. The transformation matrix has component L1, M1, N1, and L2, M2, and N2, and so forth. And if that transformation matrix is defined, the strain from new coordinate system to old coordinate system are defined based on the same rule of transformation we defined for the stresses. Again, notice that half of the shear strain are placed in these matrices, both with a new coordinate system and old coordinates. That is the benefit of understanding tensors of second degree. Many parameters in physics are defined in terms of tensors. In fact, per Einstein, every real quantity should be expressed in terms of tensors, either tensors of 0 degree, first degree, second degree, or so forth. We have examples of tensors of second degree that you have seen in your dynamics courses. And that is moments of inertia, mass moment of inertia, or the area moment of inertia. Those are also the tensors of second degree. If moment of inertia with respect to a coordinate system is given, it has 6 components. Moment of inertia with respect to x, with respect to y, with respect to z, and product of inertia with respect to x, y, x, z, and y, z, similar to the stresses and strain that we define. And rule of transformation would be exactly the same thing as we have mentioned for the stress and strain. We can see those who have composite course with me that coefficient of thermal expansion for composite material is a tensor of second degree. If you look into electricity and electrical engineering, you would find also their magnetism is a tensor of a second degree. And there are many, many examples. And those who have probably composites course with me, they would see that also material property or the stiffness or the compliance of the material would be formulated as tensors, but those are a more complicated tensor. It would be tensor of fourth order. And they have their own rule of transformation and formulation. So basically every quantity in physics would be explained in terms of tensors of the 0, first, or second, or higher degrees. All of them behave the same way. Every property we mentioned here would be also applicable with, for example, moments of inertia. There are 3 mutually perpendicular directions about which moments of inertia are either maximum or minimum, and the products of inertia are 0. Right? All right, by this discussion, we complete our session today. I insist, please work on the homework problem assigned. Complete them before the end of today. And wherever you are, whatever you did, place it in the canvas. And if you have any further question, let me know. Otherwise, you are free to go.
Thank you, Professor.
Bye-bye.
Thank you.